Hi everyone, welcome back to my YouTube videos. In this video, I'm going to show you how to simulate using a computer a discrete random variable from its probability mass function. So I'm going to start with a little bit of math at the board to show you the algorithm, but then at the end of this video, I'm going to show you an actual computer program generating a discrete random variable. So first, let's call our random variable x. Then if it's discrete, then it's characterized by its probability mass function. So I'm going to write that the probability that x equals k is equal to p sub k. So those terms are the ones that are important. That's the one that describe the random variable itself, and that's the terms of the probability mass function. And so to generate that, so the first thing we are going to do is regardless of the language you want to use, your computer should be able to generate a number, should be able to choose a number uniformly at random between 0 and whatever. The whatever is typically a power of 2 minus 1, so that you choose a number uniformly at random from a set of 2 at the power n elements. So of course, like other language would be more sophisticated and would be able to generate that directly, but I'm going to show you how we can do it from scratch using a very basic language. So the starting point is to say that the only thing we know that the computer knows how to generate is something that I'm going to call un, and un is basically a uniform random variable on the set 0, 1, and so on up to 2 at the power n minus 1. Okay, so the range here is 2 at the power n. Typically, this 2 at the power n is very large, and so to get this, at least in C, you use the command rand. Okay, so now that you have this, what we want to do from that is get eventually instead a uniform random variable, a continuous uniform random variable on the interval 0, 1. And for that, you see that here you just have to divide this un by 2 at the power n. And that's not going to give you exactly a continuous random variable on the interval 0, 1, but the new range is going to be 0, 1 over 2 at the power n, 2 divided by 2 at the power n, 3 divided by 2 at the power n, and so on. And that's going to give you a very, very small like subdivision, and that's going to be basically a very good approximation of the uniform random variable on the interval 0, 1. So once you have this, you can just look at un divided by 2 at the power n. That's the number of terms here. And so this thing, again, strictly speaking, is uniform on a finite set, but I'm going to say that it's almost uniform in the interval 0, 1. So now what we want to do from that is how can we generate this object x if we know only a uniform random variable. So I'm going to call this one u. So again, strictly speaking, no computer in the world can indeed generate a uniform random variable in the interval 0, 1 because computers don't like infinity like we do in math, but still this is a good approximation of that. Now, there is also a question mark about the randomness. A computer is not able to simulate something at random. That's instead computers are using what we call pseudo-random generator, but I'm going to tell you a little bit more about that after. That's another point. That's not about the algorithm. So, okay, so now we know how to generate a uniform random variable. This one is generated at least in C using the command rand. And to get this one, you need to divide by this 2 at the power n, and there is a name for this one. It varies depending on the version you use, but this one in C is called rand max. So if you look at rand divided by rand max, that's going to give you a good approximation of the uniform. Now, next question, how can we simulate this one from a uniform? Well, this one is really about math. It's you take your interval 0, 1 here, let's say, And so now what you do here, you take a number uniformly at random here, and you see that 1 is in fact the sum also of those pk. These are the terms of a probability mass function, so that means that the sum of the pk is equal to 1, and so what we are going to do is that put like those pk's on this segment line here of length 1. So let's assume that the range is finite and not too big, and so what I'm going to do is let's say put p0 here, and here I'm not going to put p1, I'm going to put p0 plus p1. I want this length here to be equal to p1, so maybe p0 plus p1, and maybe here a p0 plus p1 plus p2, and here we are going to have at 1, let's say p0 plus p1 plus p2 plus p3. Let's say that we have 4 possible outcomes for these random variables, like the range is 4. So you see that in this choice of those numbers, the length here is exactly p0, the length here is exactly p1, here we have p2, and here we have p3, and they add up to 1. And so now the way you generate this is just by observing that if you take a number uniformly at random in the interval 0, 1, the probability that this number is in this first interval is exactly the length of this interval, like the Lebesgue measure of this interval, so that's p0. The probability that u is in this second interval, that's going to be p1. Probability of being here is p2, probability of being here is p3. So eventually, what we obtain is that x can be viewed as, can be constructed from u by saying that x is basically going to be equal to the indicator function on the event that u belongs to first, second, third, or fourth interval. So that's the math. Now, how can you do this using a computer? I think a better way, I mean, of course, again, a computer doesn't really know what is an indicator function, so the way you can translate that more easily is just by saying the following. You start by assuming that x is equal to 0. Okay? Then you test whether u is less or equal to p0. And you say that if u is larger than p0, then you are going to add 1 to this random variable, okay, to this variable x. And so you say condition u larger than p0 is going to imply that I'm going to write x plus plus, meaning you add, so that's also some notation in C, that's what you do to add 1 to this random variable. And then that tells you that this condition tells you that your random variable is not equal to 0, that's on this side. But then you need to test again for the next value. And so you say that if u is also larger than p1, then you add again 1. And then you need it here once more. No, it's not p1, it's p0 plus p1. You want to be in the second interval. So p0 plus p1, then x plus plus, and then last condition, if u is also larger than p0 plus p1 plus p2, then you are again going to add 1 to your random variable x. So let's make a test. Let's assume that you choose a number uniformly at random and this number is here. So the probability that this number is indeed in this third interval is p2. And so we want in this case to have that x equals 2. Is it the case? Well, you start with x equals 0. Is it true that u is larger than p0? Yes, it's true. So you add 1 to x. So at this point, x is equal to 1. Then second test, is it true that u is larger than p0 plus p1? Yes, it's true. So you add again 1 to x. Now, after this implication, x is equal to 2. Is it true that u is larger than the sum of 3 here? No, it's not true. So we don't do that. We stop at x equals 2. Indeed, we have the result we want. Okay, so that's the trick to generate like a discrete random variable from a uniform random variable. So now I'm going to use this trick in another video, the one where we are going to try to simulate branching Galton-Watson branching processes, where we have this kind of offspring distribution here with different pKs. But for this video, I'm going to start slow, and I'm just going to show you a program to generate a Bernoulli random variable. And so for the Bernoulli random variable, I'm going to do something a little bit different because the parameter is characterized by p. So let's assume now, let's look at the particular case where x is Bernoulli with parameter p. So in this case, it makes more sense. So you see here, the way we give values to x depends on the position of u on this interval, and that's going to be 0, 1, 2, 3. Now, if you have a Bernoulli, what makes a little bit more sense is to reverse. So you are going to have a range only of 0, 1, and it makes a little bit more sense to exchange the roles of 0 and 1, and so you are going to obtain the following. So you take again the interval 0, 1. Now you are going to look at p here somewhere, so maybe p is here. And now you see that the first interval has length p, that should be the probability of your random variable, your Bernoulli random variable, to be equal to 1. And so now instead we are going to say that the value 1 appears, I mean x is equal to 1 if u is in this interval, but x is 0 if u is in this second interval. Okay? So, in which case, your algorithm instead becomes something like this. You can again start from, let's say, x equals 0. And then you only test whether u is less or equal to p. Now, instead of looking at whether u is larger than each of those ones or larger than p, at the opposite, you look at whether u is less than p. And so you say that if we have the condition that u is less than p, then you are going to add 1 to x. If this condition is not true, then we do nothing. And so indeed, we are going to have that x is equal to 0 if this is not true, which means that your uniform random variable is in this interval. But if u is less than p, which occurs with probability p, then in this case, indeed, x is going to be equal to 1. Okay, so that's the general trick to simulate typically any kind of discrete random variable if the only thing your computer can do is generate a uniform random variable on the interval 0, 1. So everything I talked about here is completely rigorous from a mathematical point of view. If u is indeed uniform, continuous random variable that is uniform in the interval 0, 1, now there are just two little approximations in the story. Again, in fact, we don't deal with that, but a uniform random variable on a subdivision of the interval 0, 1, but that's a good approximation. And second approximation also is the fact that a computer cannot, in fact, generate something at random that pseudo-random, but still, it's better to have pseudo-random that can do millions of operations per second instead of having to roll a die 1 million times, where you have something that is actually random, but you don't want to roll a die 1 million times. So that was kind of the theory behind. Now, in practice, you can easily generate random, like discrete random variable, all kinds of discrete random variable using this construction. This works well if the range is small, when the possible number of values of x is not too big. In another video, so that's going to be the one about White-Fisher model and Moran model. Instead of using this approach, we are going to use another approach, and that's going to be to generate a binomial random variable with first parameter n very large. For this kind of random variable where the range is very large, you don't want to use this trick that's too consuming in terms of calculation for the computer, but instead there are other tricks you can use, and I'm going to show you this in another video. But so right now we are done with this, so now let's look at an actual computer program to see how we can generate a Bernoulli random variable. So here is a C program that you can use to generate this Bernoulli random variable with parameter p. So starting from the top left, I include some libraries, that's basic stuff that we need all the time. So I'm not going to really comment on that. All the programs I'm going to show you start with that. Don't worry too much about that. Then after we define a parameter p, in this case that's 0, 1, that's going to be the parameter of our Bernoulli random variable. So here 0, 1 means that I'm going to generate the flip of a fair coin, but you can change this parameter p into whatever number you want between 0 and 1. So after I need to declare also a few things. So an integer b is going to be the outcome of our Bernoulli random variable, and a float for real number u. And u is going to be our uniform random variable. So then the little subroutine you see at the bottom on the left is exactly what you have to use to choose a number uniformly at random in the interval 0, 1. So again, I'm going to comment a little bit on this one right now, but this thing appears in all my next videos. So I'm going to spend time explaining what it is right now, but after you will know for all the other videos. So first, I'm calling that uniform because that's taking a number uniformly at random in the interval 0, 1. You start by declaring that as a float because you want to make sure that your number is indeed a real number in the interval 0, 1 and not an integer. And then the command to generate this random variable is going to be this float of rand parenthesis divided by rand max. So, like I told you just before, rand parenthesis is just the command that is going to choose a number uniformly at random in a finite set of the form 0, 1, 2, 3 up to 2 at the power n minus 1. The value of n depends on the version you are using, but typically this 2 at the power n is pretty large, and so you are going to get a good approximation of the uniform random variable in the interval 0, 1. So with this rand command, you have a number between an integer, you choose uniformly at random an integer between 0 and something big, and this something big is called rand max. And that's the other command you see on the screen. And so if you divide by 1 max, you put a float before to make sure that this number is really something real, a real number, and not an integer like you would deal with a Euclidean division. And so eventually that's going to indeed produce a number chosen uniformly at random in the interval 0, 1. Then after you conclude with a return u, and this little program, those 3 lines are going to be used to generate the uniform random variable in the interval 0, 1. So then let's look at the next column, like on the right, that starts with int main. So I'm calling that main for main program. Int because this program is going to return an integer. This integer can be 0 or 1 depending on the outcome. That's going to be the outcome of your Bernoulli random variable. So you see also that I start this program with 3 lines where I call some kind of seed and time and rand. So I'm going to also use that in all the programs in all the other videos. And so I'm going to spend a little bit of time commenting about that right now, but let's forget about that after, because you know, you will have the explanation once for all. So here what we are doing exactly is that we are choosing a seed for our pseudo-random generator. So it turns out that a computer cannot generate randomness. Instead, that's what you generate is some kind of pseudo-random sequence. And so here in this problem, it doesn't really matter because we just choose one outcome. But let's assume that you want to simulate a stochastic process with a bunch of operations. And so you will have to simulate this process to call this command uniform many times. And so what the computer is going to do is start with what I want to call a seed. That's why I'm using the word seed at the beginning of the main program. And from this seed, it's going to generate a sequence. This sequence is called pseudo-random. And in fact, maybe a better word to describe this sequence using mathematical term would be chaotic. So a chaotic system or chaotic sequence means that if you start with two different seeds, two different initial values, even if those two values are very close to each other, eventually the two sequences you are going to get, even if those sequences are generated recursively in a deterministic way, the two sequences you are going to observe are going to look completely different. And this is going to look like two different outcomes or two different realizations of the same process. But for that, it's important that you start, strictly speaking, from different seeds. If you start with the same seed, because the sequence is not random, but chaotic and so deterministic, if you start from the same seed, you are going to eventually get the exact same sequence. And you don't want to have that, because that would mean that each time you run your program, then the realization of your stochastic process you are going to see is always the same. And so that's doing a bad job. So the idea is to use together with this pseudo-random generator that correspond in fact to some kind of chaotic sequence or chaotic system, you want to make sure that each time you run your program, the seed is not going to be the same. And so this is exactly what those three lines are doing. They choose the seed based on the time, meaning the actual time on your clock, the actual time on your computer. And so that means that if you run your program at one time, you are going to observe some kind of pseudo-random sequence. And if you run your program like 1 second after, then that's going to produce a completely different sequence. And so that's the way a computer is going to simulate randomness, to mimic randomness. Okay, so now we understand those three lines. Again, I spent some time explaining like this command uniform and those three lines, mostly because they will appear again in all the other videos. So I want you to really understand that well once for all, but then I'm going to skip that in all the other videos. So now comes the actual part where we simulate the Bernoulli random variable. That's what I explained on the board. Now what we do is, in the main program, we call u equals uniform. So we are going to call the function defined on the left, called uniform. Then that means that we take a number uniformly at random between 0 and 1 in the interval 0, 1, and then we do this test. If u is less than p, which should occur with probability p, then we fix b equal to 1. Else, if at the opposite u is larger than p, then we are going to set b equals 0. And so indeed, this is going to generate your Bernoulli random variable with parameter p. Another way to proceed is what I did on the board. You can, from the beginning, for instance, say that b equals 0, and then say that if u is less than p, then you add 1 to the value of b. Eventually, the two programs, they have the same speed about, so it doesn't really matter. And then I just conclude with a printf command. The printf command is going to print on the screen the actual value. So you have a %i to say that what you want to display is an integer, and what you want to display is this value b. So that concludes explanation about this program. You see now how to generate at random a Bernoulli random variable with parameter p. Now what you can also do easily, I'm not going to do that in my programs, but something you can do is add a loop in your program, so that instead of generating one Bernoulli random variable, you are going to generate a bunch of them, and I'm sure that C can generate like 1 million of them in only 1 second. And if you do this, here is the kind of thing you get: a bunch of zeros and ones at random.